positions, we don't know where the ortho is. Right? So you need to define one of those positions. Right? We got our ring. Not to give too much away, but I think I need to draw that a second time. What's going to be substituted on the ring? Okay, we're going to put a nitro. Where do we want to put that nitro? Would it be helpful if we had a numbering system? Where do you want to put the nitro? Okay. I heard a 2, and I heard a 3 or 5. So there's really only 2 possibilities, right? Okay. So why would you say putting it at the 2 position? What's that? I'm going to have a problem with you calling that electron withdrawing. Our electron withdrawing versus electron donating all go back to a comparison to hydrogen. So we're comparing carbon of the isopropyl group to hydrogen. Carbon is more electron withdrawing than hydrogen. They have roughly the same electronegativity. If anything, carbon has more electrons. Carbon's actually electron donating. So not a withdrawing effect. If it's donating, where would it donate electrons to? Which positions in the ring would become activated? The para and ortho positions. Could we do the substitution at the para position? No. Remember, EAS is trading for a hydrogen. What we have at the ortho position is a CH3. Or sorry, the para position. So we can't do a substitution at the para position, which means you got to go ortho. Oh, okay, that's where we put it. So you were saying ortho to the isopropyl group was your product, where you should expect the nitro.
Would you substitute all 4 positions?
We could never do it all at once, so let's make the assumption, number 1, only 1. Stick with 1. We can talk about doing it multiple ones in a second.
I think 3 is better because of Steric.
And you're saying 3 is better because of sterics. Well, which is more important? Electronic effects or sterics? Electronic effects.
Which is the electronic effects between the isopropyl and the methyl virtually the same.
Since our electronic effects of the methyl and the isopropyl are almost identical, okay, we can ignore the electronic effects. Does that necessarily impact where the nitro goes? So the methyl would direct where?
3 or 5.
Para to it, which is, as we've numbered it, our position 1, or our positions 3 and 5 to be ortho. Okay, so that's how we're getting those 2 answers. Okay, our isopropyl directs para or ortho, the methyl directs para or ortho, and we end up with 2 possible substitutions, 2 possible products.
Is there a possibility you get no reaction out of this?
Yeah, but that's kind of a cop-out. So we will get some type of reaction here. So if the electronic effect is null and void, then we have to look at sterics. Which product generates the least sterically hindered? The 3,5. So we would predict the 3,5 to be our product. So we have competing donating abilities. Okay? Based off of that information, we end up picking one product over the other because our electronic effect kind of cancels out. So we're really just looking at anything else that would contribute. Sterics is a good thing to look at. How about the next one? Where would an isopropyl direct?
6 and 4.
We'll go para or ortho. Where would our methyl direct? Para or ortho. That's interesting. The three arrows I drew all overlapped. Okay, so we could potentially see the nitro going there. The nitro going over here, or the nitro going over here, which was conveniently occupied. So what do we think? We got 3 products this time.
Yeah, because you can make a steric argument, but it's also the pair position to the isopropyl.
So we have a para and ortho favoring here, but we have a para and ortho favoring on the other one. What about the first one? Both of those are ortho. Para is more favored due to sterics, so the first one should be eliminated. Between the next two, they're both para-ortho in their relationships. Para to one, ortho to the other. Okay, but there's a steric effect that is larger where? On the third one, between the nitro and the isopropyl. That steric effect does what to the energy of that product? Makes it higher in energy, which then suggests middle one's our product. Kind of makes sense? Okay. Between these two reactions, which one would we expect to have a higher yield? Second one. Why? We have a para direct favoring. Is there another argument we could make?
The nitro group is in the pair position from the isopropyl, so we have the most electron dense regions opposite each other. So this is argument.
Okay. We could make another steric argument. I would argue there's another one. In the top case, our substituents, how many favored the location of the nitro?
1 each.
1. In the bottom one, how many favored the location of the nitro? 2. The bottom one should be more electron rich than the top one. We have donating groups that are actually overlapping each other. If you will, we've got constructive interference, and we would have a bonding orbital if we wanted to tie all the way back to molecular orbital theory, which I'm sure you wanted to do. Okay. So the bottom one we would expect a higher yield because we have kind of a dual favoring there. Kind of makes sense? So back to your question about would we expect, say, in that top one, 4 nitros to substitute? What do you think? Do we think we would get multiple nitro substitutions? We have 2 donating groups.
No,
Why not?
because that's an electron withdrawing.
The nitro group itself is electron withdrawing. It is one of the most, if not the most, electron withdrawing group. That is going to make it very difficult to do a second nitration. Okay. I wish I could remember the structure, but there was a lab that I wanted to do that was kind of neat because it produced a product that would change colors, and it needed to be a dinitration. We needed to nitrate the structure twice. To do so, we had to use fuming nitric acid. So you've heard of concentrated nitric acid? What is fuming nitric acid?
It's the gas.
It is so concentrated, it is actually off-gassing nitric acid. Yes, it is very, very concentrated. Okay. Which was kind of fun to work with, primarily because I had to make it too, which was even more fun. Because the other part with nitric acid is it can form explosive materials rather quickly. So yeah, that was an interesting lab. Unfortunately, it failed because that could have been fun, but oh well. So, questions about that? Yeah, we get the answers. Steric directing effects and or reversibility. How do you make that product? What changed? Substituted a bromine. How do we substitute a bromine? Cool. Where would the bromine go? Para position. Is that where the bromine's supposed to be? Nope. So what does that mean?
Something else happened.
Could you block
So that didn't work. What do you mean block the?
the para position?
We need to do something that position is then nullified as far as its reactivity. So that it's no longer a hydrogen. So, not only do we have to do that, but then we have to be able to run our bromine reaction. And then what? We have to undo whatever we did. So do and undo, but do not. As long as a couple people get it. So, what do we have to do?
Add in something that will also leave well, like a good leaving group, but add it in.
We need something that would attach to the structure, but then is also easily reversible or leavable. Okay. This was in that exciting lecture last week where we just went through all of the reagents.
Put a chlorine on?
How do we remove the chlorine? I don't know either.
We put OH on,
Okay, how do you remove the OH?
turn the water.
Put a
But then it would need to be a leaving group, and you would leave a carbocation. Can you have a benzene carbocation?
the N triple on N. Put that on.
Okay, so there is a possibility.
And then you can
So,
go
yeah.
back to an H.
What do we do? The HNO3 followed by NaNO2. Whoops.
Isn't it NA?
Because you need the NH2 first on the ring. So HNO3 to get your NO2. Then you'd have to reduce that with our tin and HCl. Then we could add the sodium nitrite. Okay. And then we could follow that. That gets you to your intermediate now with your triple bond nitrogen. This was known as the
what?
Oh, I see what you're saying. The benzene, or the diazobenzene, I think is what it's called.
Benzene diazonium.
Yeah, that one. Okay, also known as our Sandmeyer reaction. Okay. We could run the bromine in FeBr3. That would go through and put on our group. Okay. How do we undo that? We have to put the hydrogen on. And since Jen's presumably looking at that slide with all the reagents, how would we undo that?
H3PO4?
Oh, was that it?
H3PO2.
H3PO2 and that's it?
Yes.
Cool, that would undo it. That works. Okay. So instead of running one reaction, we run 5.
So that's not a good idea.
It works. Okay. But is there a simpler way to do this? Yes. Yes, there is. As a hint, water and something. Over here, what was that? Not exactly H+. We got to be a little bit more specific. H2SO4 I'll accept. What do we start with? Concentrated what? Sulfuric acid. What did that reagent do? that sulfonates, we'd end up with the SO3H. We could then add the Br2 and FeBr3. Okay, even though it is sterically hindered, okay, we could at least put the bromine now at our ortho position of the methyl. Why does the SO3 not affect that?
Is it electron withdrawal?
SO3, what do you think? What is that sulfur? More electrons or less electrons than hydrogen? Less electrons than hydrogen. It's a withdrawing group. Okay? So it's not going to affect the substitution. Even if it did, where would it substitute based off of the sulfur? The meta position to our sulfur, which is exactly where we wanted the substitution to happen. Okay? So the sulfate is usually used as a blocking reagent. It'll block a position. You can then undo it relatively quickly using water and, again, sulfuric acid, just dilute. Okay? So you sometimes see that kind of reagent show up. Questions about that? And that one's a little bit shorter than what you suggested, Jen, though yours was equally valid. Okay. So let's look at this one. How do you make the bottom one? Let's just erase all that. Starting from benzene. You got any ideas on where to start? Why put the bromine on?
Because the other two electron withdrawing, you could kill your reaction.
The nitro is electron withdrawing, which means that would prevent substitution from occurring, okay, or at least slow it down. In one of these cases where we're saying just do it, the slow down argument isn't enough to nullify it. So I like where you're going with that. It's going to make a less high yielding product, but I want something better than that. There's a better argument. What if I did the nitro first?
I was gonna say, why don't you put the carbon and carbonyl group on first?
Ooh.
Because then you can have the bromine in the position. That's an electron withdrawing group, so when they go to the meta position.
I don't know if I put on the right carbons.
You added one extra.
I'll come back at it in a second. What was my last color? Purple. So if we did the green one first, what happens? It's going to direct the next substitution to happen at the meta position to it, which would be those two positions.
Then you could add your nitro,
Could do the nitro,
but
but then I'd never be able to get the bromine on because the nitro is going to direct meta as well. Okay, so not going to be able to get the bromine on. Okay, so that method is not a good method. What if we started with the nitro? What's that?
Same thing as the top.
It's going to direct the meta positions. So I could get the acyl group on,
But never move.
but again, I would never be able to get the bromine on because the bromine needs to go out here. So also doesn't work.
you could do the bromine, then the acyl, which would then direct to the meta.
If I did the bromine, and then our acyl, why would we expect it to go para?
Bromine's electron donating.
Bromine is our weird electron donating. It directs para-ortho even though it does deactivate. That puts the acyl group on. Okay. Again, we're going to run into yielding issues. We are going to get a low yield out of this. And then what do I need to do? Put the nitro on by doing our HNO3 reagent. Where would that put the nitro? in the right position.
Whoa.
Okay, I'll accept that. And then I also heard the, well, you're not wrong, so it's okay. I also heard the meta position, and I would argue referencing it as the meta position is a bad idea.
Because you start with the bromine, so you.
The bromine is our stronger activator. It's going, our nitro is going to the ortho position to our activator, the bromine. We put on our nitro.
Now, when you add substituents, does that, it's like we have the bromine and we have the acyl group, does that change? Which one is your stronger activator, deactivator?
It could. Is the acyl group? I don't know why that's funny. Is the acyl group an activator?
No, it's a deactivator.
Okay.
But I would say it's stronger than the bromine because it has the resonance.
Based off the arguments that we had looked at before, whoops, which do we care about? Come on. Oh, because I lost connection. Our activator will always trump the deactivator, and then it's the stronger activator.
Well, didn't we say the halides were deactivators?
Well, it's still a stronger activator.
Because it goes to the parent.
Yeah. Or a weaker deactivator. So yeah, your yield may not be great, but it's there. Okay. So when looking at these kind of synthesis questions, what you should be doing is thinking about the list of reagents we've got. Okay. There was something like 10 of them. It'd be convenient if it was the next slide, but it's not. We had a list of, I don't even think it's 10. I think it's 7, maybe 8 EAS reagents. Okay. Most of them are relatively straightforward, and you can recognize the piece that's missing and say, okay, if I put that on, where does that then direct? Oh, that doesn't set me up right. Try a different one. Try a different one. And it is that kind of recursive method of putting it on, shifting, trying again, that's going to set you up and get through these types of syntheses. Okay. The ACS does like testing on the EAS mechanism for synthesis because it doesn't really require a lot of knowledge on the reagents. Okay. The reagents tend to show up as part of the final product structure, obviously, so they can just reorganize how they're putting those pieces on. Okay. Make sense? Okay. Wish I had a few more practice ones on that, but I don't, so we'll just move on. We're now moving into some kind of last minute stuff. We can reduce an aromatic ring. Okay, what does it mean to reduce? Add hydrogens by
Or electron.
increasing oxygen bonds to reduce, decreasing oxygen bonds for a reduction. So if we take a look at benzene down at the bottom, how many oxygen bonds did I remove? None. So what was our broader definition? Electronegative. What electronegative atom did I lose? What do you mean a pi bond? Getting at the right idea. That's not an atom, though.
No, but it's, pi bond's more, has more energy.
The carbon of a pi bond is sp2 hybridized. What is the difference between an sp2 carbon and an sp3 carbon? It's closer to the nucleus. An sp2 atom is effectively more electronegative. So in the reduction that we're showing in that bottom reaction, we are losing electronegative atoms. Okay? We're changing the hybridization. Okay, so that is happening there. We're also adding hydrogens. We're adding 2 hydrogens to the structure. Yeah. So now the question becomes is how did we do this? Okay, you'll notice that the product has the double bonds not conjugated. Why might we expect that? What if it had produced the double bonds conjugated? What is that going to do about the reactivity of our hydrogens? It's going to make them very reactive. Okay? Because if we remove those hydrogens, what can happen? Resonance, and I have aromaticity, everything's fine and dandy and happy. So to do the reduction, we will remove a double bond, but we have to remove it in such a way that we remove conjugation altogether. Okay? How easy do you think this process is going to be? Not easy. Not only are we losing aromaticity, but we're also removing conjugation. Okay, this is a difficult process. It requires some relatively high energy materials, like sodium metal. Not sodium ion. Do not get confused with that. We're looking at sodium metal. I kind of accented that in the bottom case by showing an electron. Okay, sodium metal has an extra electron. That is very rare to get shown. In fact, it's typically not shown, and what you would see is what's shown up top. You see Na, the symbol for sodium, and S because it is solid. Okay, so that's in its elemental state. It has that extra electron. It is that electron that sodium is trying to ditch as fast as possible that is initiating this reaction and causing it to go through and do this fancy reduction. You all remember the mechanism for the alkyne reduction, right? Yeah, I didn't think so. I don't really remember it either. Okay. That's kind of a lie. I actually do remember it, now that I think about it. Sodium wants to ditch those electrons. What's the most reactive thing it could ditch those electrons to? Pi bond. What is reactive about that species? What's that? Yep. It is a radical. Anything else?
You have a ionic bond
I have an ionic bond. Why is the ionic bond interesting?
because it is not a very stable bond.
What charge does the carbon build? We're looking at a negative carbon. What's the most reactive thing there?
A negative carbon.
Negative carbon. What does the negative carbon want?
Electrified.
Something positive. Sodium is not good enough as a positive to stabilize it, so it needs to find a positive somewhere else. What else is out there? Okay, the NH3. We can pick up electrons. We end up now, whoops. Why would we expect the trans formation to start forming? In the case of the anion and the radical, okay, we have effectively p orbitals. Those p orbitals will facilitate free rotation about those R groups, and those are going to align as far away from each other as they can get. Okay, as soon as we initiate that sodium reaction, the R groups are going to push the opposite direction of each other to free up that steric stress. Okay. Once I've got the radical, what can now happen? I bring in another sodium, and I initiate the cascade again several times over, and I end up with the trans alkene. Okay. This is a fun reagent to remember, primarily because most reductions result in cis additions, or syn additions, or cis products. Notice here, what are we getting? The trans or the anti-addition. Okay, so we have to be a little bit more careful. This is one of the only reagents that does this, which is one of the reasons why it tends to show up fairly frequently. Okay, what happens? There it is all the way out. Nope, don't look at that. What happens if we instead did this with the aromatic ring? What's that? Good point. We don't have any rotation to worry about. Okay, so that should simplify things. So we aren't going to see necessarily a cis versus trans issue pop up. What's the sodium going to react with? Pi bond. So let's initiate. we have resonance. Right? That resonance is, interestingly enough, going to align in such a way that we get the radical being as far away from the anion as possible. The result is the basic skeleton structure of our final product. We still have to do the protonation, we have to do the second radical reaction with our sodium, but we would end up with our double bonds being on opposite sides of the ring structure. And we'd have, our final product. Kind of make sense? Okay. So we go through and look at the full mechanism, which I believe I drew nicely there. Okay. But in this case, which double bond reacted? What's that? They're all the same. So it does not matter which double bond I reacted. But what happens if I did an EAS reaction beforehand and put on a methyl group? Are all the double bonds now the same? No. Now there's a slight difference in the structure, which then means the results I get could be different. And I could end up either with one of two products. Let's ignore the mechanism stuff. Wish I didn't have that there. Could either have the methyl group attached at a position with a double bond, or where else could it be?
Where there's no double bond.
Where there's no double bond. So we get two possible products. Which of those two products would we expect? Is that a hand because you got it?
I'm scratching.
You want a hint? Wrong eraser. Let's try that again. There's your hint.
Would it be the one where the radical, tertiary radical?
The radical wants to be a little substitute.
There's no radical up there, so that doesn't help. I don't quite understand that.
I was thinking like-
radical, but you want it to be, does it want to be a little substitute position?
So you're suggesting that we should have the methyl group where the radical is because we get more substitution, right? Okay. But if the radical was there, couldn't the radical have just as easily been on the opposite side, which meant the methyl group would just as easily have been here?
Yeah, either way. Oh, I see what you're saying.
What do you mean either way? Elaborate.
So if you, let's say you start off with the radical most substituted position, you would still get a negative carbon in a tertiary position, which would not be a good thing.
We're looking at the difference in reactivity between the anion and the radical. Radicals tend to act like cations, which is why you were trying to put it at the most substituted position. But if we put the radical there, it just as easily could be the anion as well. Okay. Is the anion more stable at a tertiary position? No. So our explanation is going to come down to which is higher in energy, the anion or the radical. How do we know that?
Because you're putting two electrons close to each other.
What is the very next step of the mechanism? You kill the anion. The anion is the most reactive thing. Okay? So if our anion is our focus here, we want to make sure that it is the most stable anion we could possibly form, which means the methyl should never be located at a position where the anion is formed, which means the methyl needs to be attached to, not the radical. Remember, the radical is same part and parcel to our anion. It needs to be attached to a carbon that is sp2 hybridized. So the product we end up getting is that one. And we do not get the other one. Kind of, sort of? Because we've been doing it, switch it up. What if I did that EAS reaction first, and instead of doing a methylation, I did a nitration? Still get the possibility of two products, right? Which of these two products would I expect? Why the second one?
Because you've got a formal charge on the nitrogen and the anion attract to it.
The nitro group is bringing in a positive charge on that nitrogen. What's going to best stabilize that positive nitrogen charge? The negative charge from our intermediate. The nitro, or electron withdrawing groups, should be attached at sp3 atoms when we do the final reduction. Evaluating and understanding something about the mechanism allows us to predict where those products end up based on their charge dispersion. Kind of a neat little reaction. So here you go, 2 new questions. See what you can come up with. So when we're doing the reduction, we want to make sure that we make that anion as stable as possible. To make the anion as stable as possible, we need to keep it away from electron sources. So when we look at the very first example, what is our substituent? It's an oxygen, and that oxygen has electrons, which means the anion needs to be located as far away from that oxygen as possible, which means the oxygen is going to be located on the double bond. In the bottom case, what is our atom attached to the ring? Carbon. And while carbon is typically considered electron donating, what's the issue with this carbon? It is partially positive due to the electron withdrawing and resonance effects of that oxygen. With it being a partial positive, what do I need? I want to stabilize that as much as possible, so I'm going to bring it as close as possible to the anion, which means not on the double bond. That works. We'd end up with that as our reduced product. Kind of makes sense? Tyler brought up a good question. CH3OH, why is the methanol added? Methanol is needed to do the protonation stages. The ammonia isn't quite good enough for this.
That's why I thought it was acting as a fusion source.
We need the methanol just as a proton source. That's pretty much it. Okay. That is the one variation off of the sodium and ammonia for the alkyne reduction.
Oh, so you need the methanol specifically for the...
Specifically for the Birch reduction, which is the aromatic ring. Yep. Okay. Questions on that? Okay.
So, question, sorry. When you're saying not reduced, that just means the aromatic ring is still reduced, right?
Yes. What, and yeah, I actually hadn't even seen that interpretation before. What those arrows are referencing is the carbon of the aromatic ring. That carbon was not reduced. It still has the sp2 hybridization. In the bottom one where they're pointing out that it was reduced, the carbon that was part of the ring is now sp3. It was reduced.
So it's specific to the carbon.
Yes. Specific to the carbon in those arrows. So the last little section we got to get through is reacting, or aromatic rings, in my opinion, reacting oddly. Okay, so let's take a look at that top reaction. What happened? Did a substitution reaction. Okay. Well, we've done substitution with aromatic rings, so that's not a big deal. We did EAS. What did we substitute? Hydrogen. What are we substituting this time? Bromine. Well, that's okay because we can do an SN2 type reaction with aromatic halides. No, we can't do that. Okay, so, well, now we're out of options. Okay, so this is really weird. Why are we getting this reaction to occur? That doesn't make any sense. Okay. Bottom reactions. What's happening down there? Okay. If we erased one of those, you might be like, well, it's a substitution. just like before. Okay? Except when we unerase the other product, that's kind of weird for a substitution. Yes, we're losing the chlorine, but the thing that's doing the substitution is coming in at an entirely different location. Okay, that's kind of bizarre.
It's even meta to the activating group.
And it's meta to our activating group. So something is really weird going on with that. Okay? Both of these reactions have something in common. What is that something in common?
They're weird.
Yes, they are weird.
But they happen.
They both have H3O+.
They do both follow with H3O+. Okay, but why would you need to follow with H3O+? What are we starting both of these reactions with? Sodium hydroxide and sodium amide, both of which are strong bases. Okay. So we are somehow adding a really strong base into the environment that's also doing some kind of weird substitution. Okay. And that's the primary reason we need to follow this up with an acid. Okay. So kind of bizarre. So let's take a closer look at the top one. Okay, so we've got that base. We also notice that it is a deactivated ring. We wouldn't expect substitution to really happen on that for any decent rate because we have a nitro and a bromine, both of which are deactivating. Okay. And the bottom one, we have a mildly activated ring with that methyl group. Okay. We're still using that strong nucleophile or base. Okay, so let's break this down. What we're encountering is what is known as the nucleophilic aromatic substitution reaction, okay, or type reactions. Okay. EAS we looked at, electrophilic aromatic substitution, and that was our aromatic ring acting as in the EAS? It acted as a nucleophile, it reacted with an electrophile. Well, did it make sense for an aromatic ring to act as a nucleophile? Why are you saying yeah? It's got 3 pi bonds. Okay? That's a ton of electrons. We would expect it to act as a nucleophile. And that's why we typically see the EAS reactions as our primary driver. And in fact, if you look at the textbook used at our other campus, the previous edition of it doesn't have the NAS mechanism in its standard section. So we're looking within, 6 years? The NAS reaction is making it into textbooks. Okay, so it's a relatively new-ish reaction, though apparently they do talk about it in the appendix, which is a separate point. Okay. Why is the NAS mechanism then going to be so bizarre? What is the ring acting as? An electrophile. So with a ton of electron density, it is now acting as if it has none. That's kind of weird. Okay? So there are some conditions that we have to do to go through and adjust our reaction. The ring must be electron poor. Okay, well, if we looked at the substituents being exchanged, we added an OH and an NH2, both of which are they aren't electron withdrawing, so that's suspicious. They're electron donating groups. They're also a large source of electrons, very, very negative. So for them to react with the ring, we must neutralize the ring's ability to share electrons. So the ring somehow has to become electron poor. Okay, that's not easy to do. Okay. To make it electron poor, what can we do? Well, we can add something to it that withdraws electrons. Relatively simple. Okay. Our halogens, we're on both cases. Halogens are in that kind of weird area of deactivators, but para-ortho directors. So they are partially withdrawing electron density. But you notice in the first one we had a nitro group. The nitro group withdraws a lot of electron density. Okay. We have to have a good leaving group. This is really only going to happen with our halogens, bromine and chlorine. Okay? And we must have that leaving group located at the ortho or para position to the withdrawing group. Okay? If it was meta, no reaction occurs. To figure that out, we have to know what's going on with the mechanism. So let's take a look at a couple results here. Okay? We started with these two experiments. Only one of them produces a product. Okay? Why? To answer that, it might help to draw out a Lewis structure. What is that nitro group doing? What's that? How? Okay, so it's taking electrons away. So we pull electron density out. What charge would build on that carbon? Okay, we'd be building a positive charge there. We look at the other one. Withdrew electrons out. What charge happens to that carbon? Positive. How could I stabilize those carbons? Electrons. So I could do more resonance. What charge does that carbon build?
Never makes the bromine.
What's the problem with the structure on the left?
You're building a positive charge next to an electronegative element.
Bromine, being electron withdrawing, or an electronegative element, is trying to get electrons as quickly as it can. And yet, what am I then putting right on it, or right next to it? A positive charge. Is that a stable structure? No. So if I can somehow supply the structure with a better source of electrons than bromine, and bromine's large, it can stabilize that negative charge really well. If I add, say, a strong nucleophile like hydroxide, what can happen? I can do a substitution.
Does it come in as an SN2?
The exact mechanism of which becomes tricky. If it was an SN2, we should have seen it as an SN2 reaction before. Okay? If it was an SN1, we should have seen it as an SN1 before. Well, why did we not see either of those cases? Because it's something different. Okay. If it was an SN1, what happens?
Probably carbocation. Bromine leaves first.
The bromine leaves. If it was an SN2, what happens?
Backside.
Okay, backside attack, everything happens at the exact same instant. Okay. So here's our hybrid. The bromine or the hydroxide comes in and attacks. Starting to look like SN2, but it can't be the SN2. Something else has to be happening here. So what happens instead of the bromine leaving? The pi bond can break. And how would that pi bond break? We would end up with the electron withdrawing group pulling that electron density out, and we'd end up with, thankfully it's below both screens, it's convenient, that intermediate. That is very ugly. Okay, what is ugly about it? Lots of charge. Okay, so let's fix that. How do we fix that? Bring the electrons back down. But if we do that, what happens? We exceed the octet, so what has to happen? Kicks off a leaving group. What's our leaving group? Bromide, being better at holding the electrons than the oxygen, acts as our leaving group. and we kick it out, and we'd be right back to what we got for our final product. Okay. So what type of substitution occurred here?
SN3.
Believe it or not too far off. It's typically referred to as SNAR for aromatic. Okay. We're doing a nucleophilic aromatic substitution. There's the NAS mechanism. Okay. Kind of a bizarre little result. Why did the meta position not work? When this comes in, we can push the electrons here, but then where do the electrons go? Right back to where we were. We don't form a stabilized intermediate because the nitro group is now not located at a position that can withdraw electron density from the ring. This nullifies the attack. No attack, we can't do a later elimination. Okay. So you have to have the leaving group para or ortho to the nitro. Why para better? I know that wasn't a correct sentence. Why is para better? What is the OH acting as? I don't quite accept base. If it was acting as a base as I've defined it, it would remove a hydrogen. Is it removing a hydrogen? No, what is it doing? It's acting as a nucleophile. Nucleophiles do what? Donate electrons. If the nitro group was up at the ortho position, what does the nitro group have a bunch of? Electrons. What happens when the nucleophile gets close? We get a steric repulsion. The para substitution is going to be better for us. Okay? What happened if we go through and take a look at this separate reaction? Okay, and we compare these two. Okay. The upper one works, the bottom one does not. Why does the bottom one not work? Okay. Yes. Even if I add acid, I don't get a reaction here. Okay. It is not enough energy to clear the activation barrier to form that very highly unstable anti-aromatic or non-aromatic structure that now has tons of electron density in it. Remember, to get our NAS reaction to go, we had to have a nitro group. The nitro group is electron withdrawing. Do either of these have electron withdrawing groups? No. Okay? Which is why they fail. They don't have enough in them to help stabilize those intermediates. So to really get it to occur, we have to add tons of energy. So when we go through and looked at our substitution reactions from last semester in lab, and we run those, we didn't see a substitution, okay, with our halobenzenes because we didn't provide enough energy to clear the activation barrier for the NAS mechanism. Okay. How else could I clear that barrier if not adding heat? Light's not a bad idea, but no.
Change the structure.
Change structure of what?
Change your stirring structure to have the electron withdrawing group, lower your
Okay.
energy.
We can make our electrophile of our aromatic ring more electrophilic by putting on a nitro group. What else could we do? There's two ways to speed a reaction. Make the electrophile more electrophilic. Make the nucleophile more nucleophilic. What is our nucleophile? Hydroxide. What if we make that hydroxide more nucleophilic? What is a more nucleophilic hydroxide? Change the oxygen. How about nitrogen? How about sodium amide? See, do I have that reaction there? We run the exact same reaction with sodium amide. Okay, in ammonia, we get the substitution happening relatively readily. Interesting features. Number one, no mention of heat. Anybody know what phase ammonia is? At room temperature. A gas. How do we get it to be a liquid? Cooled it down. So not only is it not stupidly hot, 350 degrees Celsius, I've actually cooled this reaction and somehow the reaction's occurring. Why is the reaction occurring now? Stronger nucleophile. If I can't clear the activation barrier, what I'll do is raise the energy of my reactants to make the activation barrier smaller. Okay? So I can add a stronger nucleophile and I can force the reaction to occur. And this is probably what started the next issue or the next reaction. Is someone went through and tested this with other benzene structures, okay? Say with a methyl group on it. And when they ran that substitution, they expected to see one product. And instead they got two. Okay? Why is this an odd result for an NAS mechanism? In the NAS, what happens? Yes, there's a substitution. Attacks, that's already kind of problematic because we had an electron donating group there. Okay, but we end up with an intermediate with our chlorine, NH2, whoops. Right?
Call that like a direct substitution? Could you call that a direct substitution?
No, if anything, what type of reaction is that first step? It's an addition reaction. It's a loss of a pi bond. Okay. So number one, we might expect this isn't going to happen. Why? What do you mean charge? I'm putting the negative charge on a tertiary carbon. Okay, so that already starts to smack of something wrong going on here and not working. And yet somehow this reaction does work. Okay? But not only does it work, if this was the mechanism that happened, those electrons come back through, and the result I would get would be that one product. How did I get the other product? Okay, that doesn't make any sense. How could the second product form? There's only one position that's reactive. How do I get two carbon positions reactive in a synthesis reaction?
Doesn't the pi bond make it reactive?
Which pi bond?
Well, any of the pi, well, except
You're
for-
saying, so we go back to our starting material like that pi bond?
Yeah,
So that pi bond could attack the NH2?
sure.
What charge is the NH2?
Negative,
What charge is the pi bond?
negative. That one.
Okay.
Would it, so you have your first product on the left, would it happen again? And then you use the two NH2s and then it kicks out the NH, the first one.
Is there a shift?
How do I do that synthesis?
Is that hydride shift?
Can't hydride shift, I'd have to form a carbocation. Carbocations don't form on primary bromines. How do I get that synthesis to happen? As a hint. Do an elimination. Let's add a strong base. Say hydroxide. Eliminates. And then what do? Add H3O plus and H2O, or H plus and H2O. There it is. So to get a second carbon reactive, what type of reaction did I have to do? An elimination. If we take a look at our products, clearly a second carbon was reactive. So what needs to happen? What kind of reagent do I need to typically run an elimination? Shouldn't have erased that yet. A strong base. Describe to me what sodium amide is. It's a strong base. Okay, so let's do the elimination. I need the chlorine to leave, but for the chlorine to leave, something must force it off. I need electrons coming from, say, a hydrogen.
This is that pentyl structure.
What is the result of that arrow pushing?
A triple.
Did nothing to the methyl. pi bonds at the bottom are the same. That pi bond's the same, except now I have another one. What did I just form? A triple bond. That is bizarrely reactive. How might we expect the triple bond to react? As a nucleophile. Why?
It has electrons.
It has electrons. So we would expect electrons to come flying out of this structure. According to our products, those electrons are coming flying out at a negative nitrogen. What the hell is going on with this thing? Okay. Would we expect the triple bond in the ring to be a good, normal thing? Why not?
Benzenes are super stable.
Bond angles. Okay. Benzene's super stable. We can go to a bunch of different reasons, which means the electrons in that structure are now really trying to pop out to form a bond. Okay? They're really trying to get out of that structure. If the electrons are trying to come out of the structure, what are they leaving behind? Positive charge. What happens? It can either attack there, in which case I end up with that product, or it could attack there, in which case I end up with that product. I would end up forming a negative carbon. Do I have any positive hydrogens potentially floating around? Say like in the ammonia, okay, or even the H3O plus followed afterwards. Okay. This is not an NAS mechanism. Okay. It is often referred to as the benzyne mechanism. Why would it be a benzyne? Okay. I have a benzene with a triple bond in it. There's the ine ending. Okay. Yes.
Would you say like that is the primary mechanism to get both of those? Because you showed the first.
To get both those structures, yes. To get the structures that we saw back here, no.
Yeah. But just
These ones run through an NAS type mechanism. Okay. We have clear evidence to support that. Okay.
So even though for that, this one here, you showed the NAS mechanism happening for that particular reaction.
To form that one possible product, but it doesn't explain the formation of the other product, which
So-
then means
So you see the main mechanism is now your
benzyne. Yep. So as soon as you start seeing two products pop up, you're looking at the benzyne. Other things that contribute to this, for the NAS mechanism to work, we needed an electron withdrawing group attached to the ring. Do I have an electron withdrawing group? No. I actually have an electron donating group. So if you start seeing electron donating groups on your ring, you are probably running into, if you're guessing there's some weird substitution happening, you're probably running into the benzyne intermediate, and they are expecting you to predict two products. Those two products being the two shown here, where we have our direct substitution and what appears to be an alternate weird substitution, which I guess really is an alternate weird substitution, okay, because we're going through a weird elimination phase. Okay. The stuff that I find interesting about this, beyond all that. So there's our weird hybridization. Some people have referred to this as not really a benzyne intermediate, but a diradical. Okay, so there is some kind of evidence to suggest that. Okay, but we could go through and look at all of that, and we might say, okay, well, this is a bunch of load of nonsense. There's no way this could possibly happen. Okay, but we have ways to test for this. We have a highly reactive pi bond. Okay, on a structure, an aromatic ring, which we would suggest would never be reactive. Okay. What did we say the aromatic ring would never react with? Okay, this goes all the way back to the beginning of this section when we looked at aromaticity. Diels-Alder reactions and addition reactions. We said no way in hell are going to happen on an aromatic ring because it destroys aromaticity. Would I destroy aromaticity if I reacted this in a standard addition or Diels-Alder? No. So what did they go through to do? Somebody probably went through and said, you're full of crap, I'm going to test it, because if this structure exists, then it works in a Diels-Alder reaction. And then they ate their words because it worked. Okay. It could have actually been someone saying, I'm going to show you that I'm right. Okay.
And they changed it afterwards.
Yeah. So the benzyne does actually form. We have direct evidence of it in a Diels-Alder reaction. And we could also look at our standard addition reactions as well. Okay. What this then puts us to is our big summary of everything. Okay. We've got our EAS reagents. Notice the big hint with our sulfate one. That one is reversible. So we got 1, 2, 3, 4, 5, 6 EAS reagents that you need to know. Okay. We have then subsequent reactions that we could run off of those, which are also responsible for, unfortunately, most of which you've already seen before. Okay, we're just layering in more chemistry. We have multiple substitutions. They're activators and deactivators, also summarized here, which we just finished talking about today. We then also have our Birch reduction, and then we have our NAS mechanism and our elimination addition, or our benzyne intermediate. And the fun thing about putting all of that together into one slide is that we can now say that we are officially done 3 minutes late